What we're going to talk about now is we're going to be talking about a loop that happens to be carrying a charge or carrying a current. A current is a group of charge that's moving. The shape of the wire is going to be in a loop, as you can see here in the pink. There's going to be a charge carrying, or there's going to be a current in this loop, and we're going to pass this current carrying loop in between a magnetics, into a couple of magnets. So here's going to be a north pole, here's going to be a south pole. So you have a magnet here, and you'd have a magnet here. So the south pole would be, for the north facing magnet would be on this side, and the north facing pole of the magnet would be on that side. And what's going to happen, and obviously the magnetic field lines are going to be going from the north to the south. And what's going to happen here is that because of the current in the loop and in the presence of the magnetic field, this loop is going to rotate via torque. Now this becomes a very important model for electric motors that help our society function. And so what we want to do here is we want to calculate or come up with an equation for the torque. We're going to talk a little bit about where this equation comes from, and we're going to do that by diagramming the forces that are occurring in this example. Now, if what we see here on the right-hand side is we see a bird's eye view of what's going on over here on the left-hand side. So if we're sitting here on top, this pink line is represented by this pink bar here. All right. Here we have the magnetic field lines, the B lines. Okay. There's going to be a particular length, or really a width of this loop, all right, which is going to represent here. So we can call this distance W. The entire distance is going to be represented by W. This is going to be represented by L. So there's going to be a height, which we're going to call the length. So we have a width, all right. And what we can see here now, what we can see is going to happen is that if we have a rectangularly shaped loop wire, and if it's attached to a vertical shaft, which is what we have here, so this represents the vertical shaft, and it can be mounted in such a way that this loop is allowed to rotate freely in a magnetic field, then when a current is passed through the loop rotates because the magnetic forces act upon the loop in such a way, such that we have one that's going to be a negative force. It's a negative force because it's in the negative y direction. This is going to be our positive force because this is in the positive y direction. Now, the two forces here are going to be equal in magnitude, but they're going to be opposite in direction. And so there is no net force on the loop. There's no net force on the loop because this is in the positive y direction, this one is in the negative y direction, and they're in equal magnitude. And therefore, if you add the two of them up, you're going to get 0. You're going to get 0. So therefore, this loop does not experience a net force. However, the loop does experience a torque, and it is that torque that causes the loop to rotate. Now, when this loop is perfectly perpendicular to the magnetic field, basically sine of phi, we'll talk about phi in a few minutes, is going to be 90 degrees to the field, then the sine of 90 is going to be 1, and that's where you have the greatest amount of torque. When the loop is going to be parallel with the B field, then theta is going to be equal to 0, and sine of 0 is 0. All right? What is this phi? Why are we using phi as opposed to theta? Well, the reason we're using phi is because phi is going to be the angle between the B field and the normal. So we're using the normal, which is going to be the axis that is perpendicular to the top of the wire loop. And so this orange or gold yellowish line, orange I guess, it's kind of hard to tell, is going to represent our normal. It represents the normal axis to that. And so therefore, when a charge-carrying loop is placed in a magnetic field, the loop tends to rotate such that its normal becomes aligned with the magnetic field. So let's talk a little bit about this equation that we've come up with. So the equation we've come up with is that tau is equal to twice, this becomes your force, and then your distance. Now, we have two of these simply because we have a force going up, we have a force going down, and they're going to be working together. So I is going to be the current, L is going to be, remember we talked about, is the length, or in essence the height of one side of the loop. B is going to be the magnitude of the magnetic field. W is going to be the width of the loop. Now we do half because we're taking it from the center, right? We're taking this from the center, or from the shaft to the end of the loop. So this distance here is going to be W divided by 2. So if we measure from this length to that length, that's going to be all of W. But we're only looking at half of it. We have two of them, one for this side and one for that side. That's the reason for the 2, and then sine phi. Now if you take a length times a width, you end up getting an area. You get an area. So the torque, tau, is equal to the current times the area times the magnetic field times the sine of phi. All right? If you have any questions, please let me know.